Everybody, my name is Professor Soborno, and this is like really hyped up because of what I've seen lately. Anyways, today we're going to be doing some waves. I have to calm myself down so I can explain a little slower. So today, I'm going to be doing waves. So, you might ask me, Soborno, we already did waves. Why are you doing them again? Okay, that skit is probably unfunny right now. That's because we're doing a part 2 to this. Maybe a part 3 and part 4 as well. Anyways, let's look under the surface of waves. Our lesson plan for today is we're going to be first learning about some characteristics and properties of waves. And the second thing we'll learn about today is how waves are affected by different objects. So, first let's look at the first thing we're going to learn today. Characteristics and properties of waves. Now, there are a lot of characteristics. I'll show you a few right now. First of all, there's speed. You should know that by now. Second of all, there's frequency. I'm going to define them in a bit. Third, there's period. Then fourth, there's amplitude. Fifth, I believe there's also wavelength. Sixth, there's refraction, and 7 is diffraction. Keep in mind what this one means so people with no clue about how science works don't use it against you. Anyhow, okay, it was scared my mic fell off because I did a slight tug on it. Anyhow, we're going to define these now. You should probably know this, so I'm not reading speed out loud. Okay. We have frequency, which is basically the frequency of a cycle completion, also known as the inverse of t. T, which represents period, is how long it takes for a cycle to pass in seconds. Time it takes for one cycle. A is for amplitude. Amplitude is, I believe, the maximum height of oh my god, you're back! I missed you, Mr. Alex Rodriguez. Oh my god. So relieved. After 50 lectures I hadn't seen him. Now he's back. Phew. No problem. I'll leave you later, Mr. Rodriguez. Sorry. Anyways, maximum height of... Okay, so the maximum height of a wave. Waves go like this. So the maximum height of a wave would be at its tallest point over here, for example. So from 0, or where it started, to over there would be the amplitude. Then we have lambda, which stands for wavelength. Come on, inventors of waves. You can't just be so funky like that and decide to give everything except wavelength, which is the most pivotal thing, a English name, and then give this a damn Greek name. Now all the math students are going to be scared of it. Anyways, wavelength is basically just the distance between two crests or troughs. Two crests for failed Republicans. I think you didn't listen to that, Mr. Alex Rodriguez. You want to hear the definition of wavelength one more time?
Yeah.
Okay, the distance between two crests or failed Republicans.
Oh wow, nice analogy.
Yeah. So, refraction is when waves go funky because of varying mediums. They're traveling through different mediums, or their density, the density of their current medium is not constant. Now, diffraction is when waves bend due to only a small gap in an aperture. I believe these are the 7 characteristics of waves, and now we're going to be looking at the wave affection due to obstacles. So, I'm going to erase a lot of this. Well, we need to erase all of this. So what do? Well, I'm going to edit this on YouTube and it'll look hilarious. By the way, is it just me or does the spray look weird? There, that's better. Okay, so now we're going to be looking at the waves affection due to obstacles. How do waves get affected due to obstacles? Well, let's say you have water. Now, light gets bent, but it also travels a little slower in water. Maybe you didn't notice that first time. But it travels a little slower in water. So, now, how did that work? Well, it's strictly governed by, I believe, the index of refraction, and secondarily governed by the speed of light in a vacuum, which, if you don't know, is estimated to be 2.998 times 10 to the 8th power meters per second, by the way. That means in 2 seconds, light could cross the entire circumference of the Earth 15 times. Not once, not twice, not 3 times, not 10 times, 15 times. I think you're going to be pretty impressed by that. Well, it's Well, it will only cross the Earth, I believe, 14.96 times, but hey, that doesn't make a big difference, will it? To put in perspective, this is the circumference of the Earth, and this is the speed of light. It's like a magnitude and a half bigger. Anyway, I know that term doesn't exist, but still. Anyways, the velocity of light in a liquid, which I'll handle as VL, or V liquid, is equal, thus, to the speed of light in a vacuum divided by n, which is just equal to 299,792,458 times the inverse of the index of refraction. Anyways, I'm going to ask Mr. Rodriguez for a value here. Excuse me, Mr. Rodriguez, can you give me the index of refraction of water and glass?
Yeah, water is 1.33 and glass is, let me see first.
Alright.
It's in the physics reference journal.
Do what you gotta do, Mr. Rodriguez.
I'll give you right now.
So relieved to see him back in my class.
For water, it's 1.33 and for glass, it's 1.6. Or
So
1.52 crown glass.
1.52. Okay. Crayon glass is used for quite a bit of glasses, including maybe your own mirror. So that means that light would travel through your mirror at about 2.998 times 10 to the 8 divided by 1.52. Now, that's a pretty large number. So I'm thinking, using my mathematical skills, I'm going to estimate it down to about 2 times 10 to the 8th power. So that doesn't really make the number even budge. It's still huge. But it still did take a pretty good chunk off of it. But again, this is division, not multiplication. So now, anyways, when you're going to be in glass, that would be about doing this. 3 times 10 to the 8 times 3/4 would be 9/4 times 10 to the 8. How would you say that? Wouldn't that be 2.25 times 10 to the 8th power? Yeah. So, this is how fast light travels in glass. Still enough to cross the circumference of the Earth at least 7 times, I would imagine. Maybe 10. And then this is how fast it would travel while I believe it's in a glass, which I believe would be enough to cross the Earth 8 times? I'm not sure. Why are we even using Earth circumferences? Anyways, it would only take like 4 years to reach Alpha Centauri. I know that may seem like a lot, but when you convert that into meters, let's see what we get. So 299,792,458 in 299,792,458 times 126,144,000. So this is what I've typed in, everybody. You guys ready? That wasn't a very specific answer, TI-84 plus. I thought better for you, Texas Instruments. Anyways, that gives us 378,170,1982. Approximately this, how many digits are here? That's equal to 9. 1, 2, 3, 4, 5, 6, 7. Around this number in meters. So since I'm only about 1 meter tall, it would take about, I believe, what is this number? 1, 2, 3, 4, 5. Well, wouldn't that be, wait, 820 million, 19 billion, 817 trillion, 37 quadrillion. That's 37 quadrillion Sobornos stacked up on top of each other harshly. Almost 38 quadrillion though. That's huge when you think about it. So that just really puts into perspective why light is so impossible to observe slow motion. Anyways, with that, everybody, let's see how long this went on for. 25 minutes, and bye.
Bye.